Here is the question that I ended the first part of this video lecture with, and it's very simple to work out. All you have to do is construct the sum of the potential differences around the loop, solve for the one we're looking for, which is the one from C to D, and plug in the numbers, and you'll easily come up with a potential difference from C to D of negative 50 volts. What we've seen is that if we know the electric field as a function of position, we can get the potential as a function of position. But it's easier to calculate potential than it is to calculate field, and so it would be awfully convenient if we could do the other way around, find the potential, and then use it to find the field. Well, we can, so let's see how. So here's a point A where we wish to know the E field, and let's say we know the potential in this region. So here's a schematic set of equipotential curves, and it's high potential over here and low potential over here. So we know in this diagram the E field would be pointing perpendicular to the equipotential curves and from high potential to low potential. And now I'm going to define an arbitrary axis. So I'm just going to stick it up this way. And this is any old axis. I'm going to call it the S-axis. And for convenience, I'm going to define a unit vector along it, which I'll call S hat. But note, this could be our x-axis, in which case this unit vector is I hat. This could be our y-axis, in which case it's j hat, whatever. But there's some angle here between the axis and the E field. And we will now imagine taking a charge from A and moving it some small distance, which I will call delta S along here. And so this is the delta S vector pointing along the S-axis. Now let's think about the electrostatic work done on this charge as we move it along this vector delta S. Well, that electrostatic work is going to be approximately the electric force dotted with delta S. And I say approximately because the electric force is not guaranteed to be uniform because this E field is variable. So it's approximately QE dot delta S. That is just Q times the magnitude of E times the magnitude of delta S times the cos of the angle between them. And E cos theta is just the component of the E field along the S-axis, what we would call ES. And so I'm going to write it that way. The potential from A to the end of delta S will have changed by some small amount that I'll call delta V, and that would be equal to the negative of the electrostatic work done on the particle divided by the charge on the particle. And so that is approximately all of this expression over Q. And so, as always, the charge, we're thinking of this as a probe charge, has to cancel out. Well, this tells us that our S component of the E field is approximately delta V over delta S. But now if I take the limit as delta S goes to 0, this is going to become precise, and I just see that the S component of the E field is negative dV by ds. Let's use what we just found, and we'll use it for the uniformly charged thin ring. So in lecture 4, we found the potential as a function of z along the z-axis. And that means we can use that to get the E field. We can say that the z component of the E field at a point on the z-axis is going to be the negative of the z derivative of the potential as a function of z? Well, that derivative is not too difficult. I'm going to just pull out all the constants. And if you recognize that this 2 pi lambda r is the circumference times the linear charge density, you can see that this is kqz, which is exactly what we got back in the electric fields unit for the electric field due to a thin ring.